with no further ado, we'll have Rick Thoman, and we'll let Rick introduce himself. He's one of Alaska's leading climatologists and a lot of great stuff to say, and he's here to talk to you about the future and the past and the present of climatology in Alaska as our keynote address. Thanks so much for being here, Rick. It's an honor to be here in Duncan. Thank you.
Thank you.
Yeah.
Okay.
Great. Thanks very much, Eric, and thanks to everyone for coming. So good to be back at WAISC in person. So yes, I'm Rick Thoman. I currently work at the Alaska Center for Climate Assessment and Policy, which is one of the groups within the International Arctic Research Center at UAF. This was supposed to be my Walmart greeter part-time retirement job. I spent more than 30 years with the National Weather Service here in Alaska, and it soon became apparent that it would be another job, but it would not be a part-time or a Walmart greeter type of position. So I'm just as busy as before. I just get my paycheck from somebody else. So in a sign of how old we're all getting, I recently calculated that I've been working in weather and climate now for professionally for 40 years, which is kind of hard to believe. Nearly all of that time here in Alaska. So really happy to be here. UAF, of course, and IARC and ACAP, we are on the traditional and never ceded lands at Troth-Yitthak, traditional lands of the Tanana people, and very happy and honored to be here in Yupik country. All right. Next slide. Okay, so if I do nothing else, I'm going to attempt to keep the being on time streak alive here. So that would be the definition of success. I really have three main themes here. I'm going to start out with a review of how our climate here in Alaska, climate at large, is changed in the recent decades. Going to spend some time on extreme events because that's really where the money, so to speak, is in the next couple of decades, and finish up with just a brief look at the future that many of you in this room are working to make better. Next slide. But first, a little bit more about myself. Imagine there's a Pennsylvania Dutch boy, and he's really into weather, and he's really into Alaska. Growing up in southeast Pennsylvania, not a cold or snowy climate, occasional big snowstorm, but I just ate this stuff up as a kid and as a young adult, and I was just intrigued by the environments that these and other books write about. Now, I've gone back and I've reread all of these as an adult and as an Alaskan, and yes, there's lots of problems with them. Absolutely. But the descriptions of the environment still are evocative to me. And next. Go back one. This guy changed a little bit. Yeah, 1970s, big air was. But this kind of formed the Alaska environment that I came here more than 35 years ago, and I got some of a taste of that. Things were already changing, but I got a taste of that. For those of you in the room have born and raised here with deep roots here, you know from your own experience, you know from your families, your communities, your tribe stories, how much things have changed. Next slide. So let's dive into our changing environment. So just to be clear, one slide, just to make sure we're all on the same table here, weather versus climate. This seems like this should be a pretty simple thing, but it's a confusion between weather and climate that allow people to say, it's cold out there today, so gee, climate must not be changing. Why someone can bring a snowball into the United States Senate and say this proves that the climate is not changing. Weather is, in its purest sense, the instantaneous state of the environment. What's the temperature right now? What's the precipitation right now? Now, in fact, we use it in a little bit broader sense, but in the purest, in this most simple sense, that weather is just the right now, or at a specific point in time. Doesn't have to be now. The weather conditions, the atmospheric conditions on the minute that you were born is part of weather. Climate, in its most basic form, is nothing, absolutely nothing, but the statistics of weather. So we think about things like the low temperature this morning as part of weather, but it's actually not. It's part of climate, because you can get out your Excel spreadsheet and you can have the temperature every single minute today, and then you'll put in min of this. That's a statistic. So if you can make a statistic out of a whole bunch of instantaneous states, measurements, data, that's in the end, that is climate. Now, in practice, of course, we have weather forecasts at half-day intervals today, tonight, tomorrow. We have climate outlooks at weeks, months, seasons, years, decades. But it is, I think, really important because of this confusion, whether intentional or otherwise, of between the two. Next slide. Next click. So here's some things you might have heard to illustrate that difference. Maybe you weren't expecting it to be 12 degrees in Billington in early April. That would be what you expect. That's the climate part. The weather is what actually transpires. Climate is what's in your closet, and weather is what you're going to wear today. And if you're a sports fan, you might like this. You might have heard of this guy named Babe Ruth. So the long view, the statistics view of Babe's career, he was a great home run hitter. But the weather portion, the instantaneous part of Babe's career, is he didn't hit a home run every game, every time back. In fact, he had some dud days as well. Instantaneous, long term. That's really all the difference between weather and climate. All right, our changing climate. We can think about changes in a lot of different ways. Stuff that tends to get the press are long-term changes. Obviously, this could be many, many, many bullets long for all of these long-term changes. So things like temperatures rising over decades scale. Doesn't mean the temperature every day is warmer than the day before, right? That's not how it works. Doesn't mean that every than the one before. Not how it works. But when you look at decades long, we see temperatures rising. Similarly, with sea ice. Long term, there's no doubt sea ice is declining. We know from our elders that sea ice has been declining for a very, very long time. There's also changes in the seasonal cycle. So not just over the decades time, but over the course of the year. So, as I'll show in a little bit, over all of Alaska, snow is melting out earlier, on average, over the long term. That's a seasonal change. On average, over the long term, river ice is unsafe later in the autumn. Folks in the Bethel area know that this kind of open water in the week before Thanksgiving used to be a rare thing. Now it's commonly unsafe for travel on the lower Cusco into late November or early December. It's not that that never used to happen. It just happens very infrequently. And that's not like it happens every year now. 2021 actually was a pretty good year for autumn ice on the Cusco, but more years than used to be, it's not. And of course, extreme events. What's an extreme event? We're going to be talking about that a lot. If you don't like the word extreme, think of it as a rare event. rare events. How can a rare event be more frequent? Something to think about. But these extreme events are becoming more frequent and their impacts are increasing to our society. Next. All right. So this is a plot of showing the total change in average annual temperature over the last 50 years in Alaska. Now, what I'm using here is the latest and greatest in climate science. This is from basically a climate analysis model that is now at high enough resolution that we can start to see some details. This kind of product at this kind of resolution did not exist in a usable form 5 years ago. So this is brand new, and this is incredibly important. Not only does it give us complete spatial coverage, but there's been a dramatic decrease in the amount of in place, in situ climate observations around the world, but especially in North America, Alaska, and Canada, in particular over the last 20 years. And so this has really been a game changer for understanding how things are changing here in Alaska. So if you look at this graphic, scales down here, Billingham's here, Yoggovic's here, Ketchikan's over here. If you look closely, you will see there is absolutely no blue. There's no point here where the average temperature over the last 50 years has decreased. There is a small area here in the southeast interior into the central Yukon where there's not been great change. Any guess on why this would appear here as opposed to somewhere else?
Farther from the water. From the ocean, farther from the ocean.
And equally important, what else?
From the sea ice. What do you mean?
Mountains. It's comparatively far from the ocean, although in reality, of course, Alaska is just one big fat peninsula of North America sticking west. But this area here is isolated from the Gulf of Alaska by the Wrangell St. Elias, and in here, Chugach, and then the Brooks Range to the north. So this makes sense. What I want you to get out of this is, you often hear, the Arctic's warming X times faster than the rest of the world. Alaska's warming X times faster than the lower 48. And those numbers might be perfectly true. I mean, they generally are, right? But those are the big picture values, and we don't live at the big picture, most of us, most of the time. We live locally, we live regionally. And this is incredibly important as we plan for our future. We need to have this kind of information at this detail, because how things are changing on the North Slope, how things are changing in Bristol Bay are very different at this scale than how things are changing if you're in Thoman. And I think it's incredibly important to have the most accurate information for your purpose. For your purpose. And as was pointed out there, the largest changes here, North Slope, Bering Sea region, especially north of Nunivak Island, those changes are strongly tied to changes in the seasonality and the quality of sea ice. But those and the warming oceans effects extend much more broadly. Next slide. All right, that was the annual temperature. But we don't live annually. We live, day to day, right? So here's the same data over the same time periods, and now I've split it out by season. And look at the differences. In some cases, the pattern isn't even the same. Winter, spring, summer, fall. The color scale is exactly the same as on the previous map. They're all the same. And what jumps out at me here is one, summer stands out as utterly different. Why would that be? Why would it be qualitatively different than the other seasons?
Lack of sea ice?
That's part of it, but bigger. Summer, June, July, August is the one season over most of land area of Alaska where snow is not a consideration. And so we see the areas that have these incredible changes, the other seasons, like on central North Slope, have very weak changes in temperature in the summer, average temperature in the summer. The largest changes, in fact, are here in Norton Sound and Bristol Bay, extending down along the southeast Bering Sea coast. Some of this is sea ice related. What else are influencing these small bodies of water, ocean? You got big rivers emptying into all of these. The waters in the river are warming. But it's warming everywhere. Gigantic changes here, way off the scale here in the autumn. That is entirely due to the collapse of autumn sea ice. Spring is the only season when we see any area that's actually had a little bit of cooling. This isn't very much, but it's very different than anywhere, any of the other seasons. So not only is it changes spatially different, they vary across the time of the year. Again, very important. Planning for the future, we need to know not just how long-term things are changing, but how that varies through the year. Next. Now, we saw that temperatures are warming, but many things respond to not to the averages, but to the extremes. And probably the most graphic example is the spread of Spruce Bark Beetle. Spruce Bark Beetle is not an invasive species. It's been found mostly on the Kenai Peninsula for many centuries, but it was largely confined there because spruce bark beetles are very sensitive to sustained low temperatures. Sustained low enough temperatures kill the larvae and keep them from spreading. And now, just in the last 20 years, and most of that in the last 10 years, there's now significant, obvious, as you're driving along, spruce bark beetle kill as far north as Cantwell. Climate of Cantwell never been described as similar to the Kenai Peninsula. What's driving that is the lack of sustained deep 30, 40 below cold south of the Alaska Range. So it's not always about averages. Extremes matter a lot. Why don't we have maple trees natively in Alaska? Grow in Minnesota. Extremes. Maple trees do great until the temperatures get to about 40 below. Sustained 40 below, wipe them out. So people in Fairbanks regularly plant maple trees and then a couple of years later take them out and cut them down. Yeah, that's why. Okay. Next slide. Okay, temperatures. Now on to precipitation. Same graphic as before, same 50 years, 1973 to 2022. This is the change in the total annual precipitation. This looks very different in temperature. One, the changes are, for the most part, not large. There are small areas with weak trends towards less precipitation. Overall, the green colors indicate a trend towards more, but the values are very low. For the, if you prefer, most of these changes and all of the lightest shades don't reach that statistical significance, still in the noise. The exception, of course, is here on the North Slope, and you already know what's driving this. Why would they be getting significantly more precipitation on the North Slope? Say it with me. Loss of sea ice. That's you got more water exposed, more water is evaporating into the atmosphere. Bring it out. All right, next slide. Now, how about snow? Snow, now this is for the whole cold season, September through May. And this looks not dissimilar over most of mainland Alaska to the precipitation. Most areas are seeing no change. There's some areas with weak decreases, increasing on the North Slope. And you know why. Different story along coastal areas, basically Gulf of Alaska coast and the Alaska Peninsula, southwest of King Salmon, where there is a trend towards less, and these darker colors do reach that statistical significance. But overall, not a lot of change. Does that surprise anyone here? Total seasonal snowfall not changing significantly? No. Okay, you're better than me, because when I first looked at this, I wasn't expecting that. At least not over such a large area with weak or no changes.
That's when it falls. To be
What?
different. Like when it's falling.
Have you seen these slides already?
No, that's not the last.
All right. Exactly. So autumn snowfall changes,
Yeah.
midwinter snowfall changes, exact same color scale as the last one. Virtually everywhere in Alaska, except for portions of the Brooks Range and North Slope, autumn snowfall is collapsing. Dramatic decreases. It's not because precipitation is decreasing. I didn't show the seasonal breakout of precipitation because they're mostly show all not much change. But much more of the precipitation over most of Alaska in the autumn is coming as rain instead of snow. But we're mostly making up for that with midwinter snowfall. And that makes perfect sense, right? In a warming world, warmer air can hold more moisture than colder air, but the average temperature over most all of mainland Alaska during the midwinter months is still well below freezing. So it's still on average cold enough to support snow. Air can hold more moisture. The predominant form of that precipitation is going to be snow. So this makes perfect physical sense, what we expect in a warming world. At some point, starting in the south and west and working its way north and east, we will start to see total seasonal snow decrease as more and more winter precipitation comes as rain. That will probably happen soon here in Bristol Bay. It's not going to happen like in anybody here's lifetime, probably of the Brooks Range, but that will be changing. And so that has all kinds of implications for extreme events. Raise your hand if you love freezing rain. All right, well, you are going to be one happy person in the coming decades. Buy your house in Fairbanks soon, and you will be in seventh heaven as rain becomes more common and roads become ice skating rinks for 4 months a year. Next slide.
For extinguishing fires.
What's that?
There was a fire out here years ago and it lasted for 7 days in freezing rain, just like.
Rain would have done that too, right?
Not to be freezing.
That's that big November fire, wasn't it?
In 2010, a fire started at the Kanakanak Hospital and it started on a Good Friday and then it went all the way to Coffee Point and then the mouth of Snake River. And then it freezing rain after 7 days turned it on.
Great. I mentioned already changing length of snow season. This is kind of interesting. First of all, the snow length season, except if you're on a glacier, is decreasing everywhere in Alaska. So this is the start of the winter snowpack establishment to the melt off. What I don't have here, just in the interest of time, when this is occurring varies across the state. Over much of Western Alaska, the change in the autumn dates are much larger than in the spring dates. In the Susitna Valley here, where there's big changes, a lot of this is in summer. Over most of the interior, some of the inland Bristol Bay kind of split between coming later in the fall and earlier in the spring. But this has massive, of course, impacts to things like ecosystems. When the tundra starts drying out, has big impacts and ramifications for things like wildfire. Next slide. Speaking of wildfire, the Iowithla fire here, largest fire on record, close to Dillingham, almost around 50,000 acres, if memory serves. This was just last year. Of course, wildfire is a natural part of the ecosystem. Boreal forest is evolved to work with wildfire. Wildfire regime, as we know it in Alaska, it's been in place about 6,000 years when black spruce spread pretty widely. So people, thunderstorms, and fire have been coexisting for that whole time. What were the big changes that we're seeing? One, we're seeing increases in frequency, not only of the whole amount area burned, but we're seeing more wildfire in places that didn't used to have it. Right here in Southwest Alaska is a prime example. Why are we seeing bigger wildfire seasons, more wildfire in places that didn't used to see that very often? Well, it's a combo, right? Just saw the earlier snow melt, warmer springs, and with no snow on the ground, you start drying that vegetation that much sooner than in the past. But early snow melt and dry, warmer springs don't cause the boreal forest or the tundra to spontaneously combust. You need a spark, right? In Alaska, by far the most important spark are thunderstorms. And everybody in Southwest Alaska, YK Delta, says the frequency of thunderstorms are increasing. Not even elders are telling us that, but even middle-aged people are saying this used to be rare. It was a notable event when we heard thunder in a place like St. Mary's. And now we're getting it much more frequently. That is exactly what we expect in a warming environment. In Alaska, the primary hold, if you will, determiner of thunderstorms is the amount of moisture available. That's usually the limiting factor. And so just a little bit of increase in moisture in the atmosphere, warmer world, warmer oceans, more evaporation, and now thunderstorms that wouldn't have formed 40 years ago, now there's just enough moisture to pop them off. So exactly what we expect. Next slide. So here's the graphics to go with that. You may have seen some of these. On the left-hand side here, this is a plot of just the total acreage burned in Alaska since 1950. The red bars are more than 3 million acres. You don't need any detailed statistical analysis to see. Prior to the early 2000s, 3 million acre seasons were quite unusual. There were only 3 between 1950 and 2003. And since 2004, there have now been 4. This is not because of some change in fire management strategy, although the theory was prior to the mid-1980s, we're going to fight every fire. In Alaska, there were never the resources to do that. There just weren't the number of human beings to enact that. So in reality, in practice, fire management strategy, reality has been we fight fires where they threaten basically infrastructure or cultural things of value, and the rest just burn, whether that was through policy nowadays or practical necessity back in the day. The change in Western Alaska is really, really dramatic. So this is the YK Delta area burned. Alaska Fire Service has spent a lot of time trying to go back to old records, satellite imagery to reconstruct wildfire history. Now we know for sure that there are small fires missed. There was some of you may have seen a recent presentation where some really detailed work was done on the North Slope, and they nearly doubled the number of known fires, but they're all small. The total acreage increase for known wildfires on the North Slope only increased by about 1.5%, because through some very detailed work, they were able to find 5-10 acre fires kind of thing. So at this scale, these numbers are firm. We're pretty confident at this point. There are no big wildfires since 1950 that are not accounted for. And clearly something changed in 2015. 4 times since 2015. There's more wildfire acreage, more acreage has burned on the Waikiki Delta than any year prior to 2015, 4 times. And all of these are lightning starts. Warmer springs, losing the snow cover earlier. It sadly makes sense. You may have seen the same graphic for the Bristol Bay region. Last year, more acreage burned in the Bristol Bay region, which by Alaska Fire Service definition actually extends to north of Iliamna Lake, a pretty big area. But last year in that area, more acreage burned than in every year from 1950 to 2021 combined. The Cocktooley River and Pike Creek fires were the big ones, but things like the Iowa fire as well contributed to that. So a whole sea change in Southwest Alaska wildfire. Next slide. Oceans. Obviously, oceans are of vital importance to the Bristol Bay region in Western Alaska. And here's the change in July, average sea surface temperatures. North of the Bering Strait, these changes in July are mostly related to changes in sea ice and also in Kotzebue Sound into the big rivers emptying into there. But notice even over the deep oceans where sea ice is not an issue, again, everywhere is warming. Very substantial change here in the last 50, in this case, not quite 50 years, in outer Bristol Bay. 5.5 degree change in ocean water temperature. Ocean water is dense. Temperatures change slowly. That's really quite a dramatic change. And that's, of course, not ice affected by the time we get to July. Deep waters in the Gulf of Alaska, all warming. Big changes. Next slide. I could talk a very long time on sea ice, but I won't bore you. I will only say this. Changes in seasonality in sea ice are of utter, complete importance to Alaska. I don't care what the Arctic sea ice minimum is in September for these purposes. The changes in seasonality are having the biggest effect on Alaska. Here's the Bering Sea, and this is a change relative to the long-term average, and this illustrates how dramatically the autumn sea ice is decreased, now less than it used to be. In late winter, early spring, the changes in extent are more modest. Remember, extent tells us nothing about quality of the ice thickness. It's just yes or no. But even that simple metric, which we use because it's comparatively easy to measure by satellites and has been done for 45 years now. This change in seasonality, similarly in the spring, bigger changes than in early spring, but late spring, early summer, bigger changes. That is of incredible importance. The sea ice that's there is thinning almost everywhere, both near Alaska and the Arctic as a whole. One of the most moving stories I ever heard about sea ice was from Clement Ungett of Gamble. It's about 85 years old now. And he talks about how when he was a kid, so this is World War II time frame, the kids in Gamble would eagerly await the arrival of big blue icebergs in September that came down on the west side of the Bering Strait and occasionally would beach at Gamble because they were jungle gyms. They could climb all over. And this deep blue ice, it was old multi-year ice. Clement said he hasn't seen that at Gamble since the late 50s or early 60s. Sea ice has been changing, the quality of sea ice has been changing for far longer than Western science has satellite records. Very important. Next slide. Now I put the ocean bottom temperature slide here after the sea ice because sea ice is controlling so much of what's happening in the shallow waters of the eastern Bering Sea. This is from the NOAA Fisheries Race Division, their bottom trawl survey. The thing to focus on here on these graphics are that deep blue area. That's the water at the bottom of Bering Sea that is colder than 0 degrees Celsius, where salt water freezes about -1.8. about 29 Fahrenheit. So it's colder than fresh water, and it's also extremely salty. In 2010, look how far southeast here, that extremely cold, extremely salty water at the bottom of the Bering extended. That, of course, changed dramatically with the collapse of the sea ice, spring and sea ice in 2018-19. We've seen a little bit of recovery, but it's clear that we're not going back to that. This has massive ecosystem changes as the southern Bering Sea fish species move northward, and the Arctic adapted species previously in the northern Bering Sea presumably are moving northward to find colder waters, right? Fish are going to live where they can and not live where they can't. They don't care how we measure things, don't care what we do. That's just the it. Next. All right. The drive-by version of what's happened. Now let's talk about extreme events. And here's a little graphic that I made up. This is just the last 5 years of extreme events, and this is just what I could fit on this slide. There's many more, but I want to point out some unifying features. As you move your eye around on all these events, most of what I've put on here in the last 5 years are precipitation related. The 2000 teens, especially 2013 to 19, I would say were dominated by extreme warmth in Alaska. Temperatures were the big thing. Since 2019, I think we've seen a shift. Temperatures have been less extreme, but these high-end precipitation events have become come much more to the fore. So, it's kind of a big thing, right? There is some temperature things here. Those of you that were in Alaska in July 2019 probably remember the July 4th heat wave, all-time record high temperatures set. Anchorage, Kenai, King Salmon, really quite remarkable. 2019 extreme drought, widespread drought across southern Alaska. But we've had a lot of precipitation records, not just in Western Alaska. Southeast Alaska had the pleasure. Drought 2017 to 19, followed by, since then, heavy rains, including these so-called atmospheric river events that produce, for instance, the catastrophic and tragic landslides at Haines, all-time record 24-hour precipitation. So these extreme events are really taking a toll on Alaska. As a person who works in this and works to document this, I'm suffering from extreme event fatigue. That's for sure. I would love like a year of quiet weather. I'm gonna guess I'm not gonna get that. Okay? But extreme weather or climate events are not all equal. So compare the September 22 storm, ex-typhoon Merbach, widespread damage across 1,000 miles of coastline. In some places, the highest water level documented going back a century or more. Compare that to those of you from Anchorage, the December snow collapse, and 40-odd inches of snow in less than 2 weeks. Long, months-long ramifications as people, as the roads were slow to be plowed, but not unprecedented. And compare that to say if it's not going to, but if it got to 50 degrees in Billington today, that would be the highest temperature on April 6th in a century. It's a climatic extreme event, but the impacts of that would obviously be much less than snow collapse, but much less than Merbach. So extreme event by itself might be interesting from a climate perspective, but not as they're not all equally impactful. Next slide. So any extreme event takes place in some kind of context. We have the annual cycle context. One of the things that made Merbach so impactful was it was occurring so early in the year. There was no sea ice, there was no freeze up yet, but beaches, everything, was completely thawed from the summer. That's very different than the 2011 storm that occurred after some sea ice had started to form in the Bering Sea. So you saw impacts in different places. And then it's also occurring on top of the long-term changes. This is a kind of an interesting graphic. I really like this, and I apologize for the scale. But the graphic here shows areas that would become inundated if we had a 1 meter rise in sea level. And look how unevenly distributed this is. The YK Delta is extremely, extremely vulnerable to a relatively modest rise in sea level. Portions of the Bristol Bay region, especially on the Alaska Peninsula, are also at risk. Portions of Northwest Arctic Borough, portions of the North Slope. Canada could have a world of problems there in the Mackenzie River Delta. But other places, 1 meter sea level rise have impacts, but different than inundation. But all extreme events, all rare events are occurring on top of these kind of changes. Next. And so I want to use this to emphasize, I throw around extreme events, rare events, casually, but they're really very different structures and can be very complex. So, temperatures are maybe the simplest. If you have an extended period above or below some important threshold, get some impacts. Things like river breakup in the spring, river ice breakup, illustrate the unequal nature of the various pieces of the puzzle. By far, the most important thing for river ice breakup is what the temperatures are in the early spring. But other things contribute. But one is overwhelmingly important. And then you have things like coastal flooding, where there are many, many pieces of the puzzle that have to come together in order to produce an impactful extreme event like coastal flooding. So again, highlighting here, extreme events are not all in one bag. They have very different structures, and that can influence their impacts. Next slide. So this is my little Venn diagram of extreme events, and it's really when you get the type of event, where it's occurring, what it's occurring, and there's the annual cycle, the long-term change, where these all intersect. This is where the high impact events. So if it got to 50 degrees today in Dillingham, we'd have an extreme event here, but these would not be in play. Murbach, on the other hand, they all came together to produce that catastrophe. Next slide. And of course, extreme events occur over, the whole timeline from minutes. There will be Levelock wildfire, 2019. Within minutes, hour of starting, fire was burning into town. Same thing happened in Canicross some years earlier, maybe 2011 or 12. Lightning strike right in town, started a fire, and people were evacuating when 20 minutes before they were watching TV, kind of thing. On up, to years and everything in between. And of course, things like wildfire, can go from minutes to whole seasons, as in 2004. And things like erosion, we think of as building up over years, but of course, you can have catastrophic failure. So the state of Alaska is newly defined USHTEC hazard, where you have a catastrophic land loss, whether from erosion, from a frost thaw, kind of thing. So these different timescales, very important to keep in mind when we are planning for the future. All extreme events are not the same. Next slide. All right, last few slides here, futures. Okay, if you get one thing out of this talk. So here's the future comes in stages. So here is this is just random variability from something that varies along a baseline This would be best applicable for things like temperature or precipitation. So this is just some random variability. This would be an unchanging climate. Okay, now what happens if we put on something like El Nino, La Nina that has a short-term effect? Next, we get this. And so this is a time scale, maybe about the El Nino, La Nina cycle. I've made it more regular than it really is. But what these short-term cycles do is they tend to amplify the extremes. But the average of all these is still close to zero. Okay, we know there are longer-term cycles in the Earth atmosphere system. So let's throw in a long-term signal. So this is about a 40-year signal here. This would be something like deep ocean, or some deep ocean circulation type patterns. Now we not only amplify the extremes, but we now get more clustering. We get runs of, in this case, years of above or below normal when the two cycles are in phase. So when both are pointing the same direction, and they amplify the extreme. But again, over our whole time here, which I arbitrarily call 80 years, so there's the average is close to zero. Okay, this all happens in a stationary climate. Now let's put on a trend. It's not that these cycles are any less important here than they are here. But in the long run, trend obliterates everything. This is really important, I think, because if we're here, this trend, it doesn't have much effect for a while. It has some, but not very much. The next 25 years are not likely to be dramatically different in the averages. They will be creeping up. It won't be steady. We've seen repeatedly in the past, there tends to be step-like changes. For you young people, your grandchildren who are living up here, the trend is everything. There's still year-to-year variability, but what they think of as normal, what they expect will be wildly different than today. That's why this part down here where we're living now, the trend is important, but the extreme events are really the big thing. Next. You've all seen this. This is from the IPCC4. Small increases in averages translate to huge increases in the extreme events. I want to point out, in this case, let's pretend this is temperature. Slight increase in the average temperature means a big increase in the risk of high-end temperatures. There's a decreased risk of low cold temperature. Doesn't mean there's zero risk. Climate change does not mean that Dillingham turns into Maui overnight. Less risk, more risk. Slight change in the averages, big changes in the scales of the distribution. Like that. Next. So the next 20 years, the extreme events are going to, they're tied to warming temperatures, ocean and air. And we can look for things that point in that, that are tied to that. So things like extreme precipitation events, because that's tied to more moisture in the atmosphere. We have not seen the worst that wildfire can do in Alaska, and in the next 20 years, we're probably going to see that, including more fires in places where it's not supposed to have wildfire. On the other hand, warming temperatures plus just natural variability in precipitation is going to mean more drought because you've got more evaporation during the warm season. Got more plant growth, more evapotranspiration from plants, marine heat waves, coastal flooding. I may or may not live to see it, but not going to have to wait that long to see another spring sea ice like we saw in 2018-19. Even though it's been more than 5,000 years since we saw that, we are not going to have to wait very long to see it again. So as Alaskans, preparing for extremes, I think is really where we need to focus our energy. That can come in a couple different ways. Preparing for extremes we know should happen. The city of Anchorage should have known that there could be 40 inches of snow in less than 2 weeks because it's happened before. To say we had no idea this could happen is kind of just showing something else. But it's kind of maybe human nature to think, okay, whatever it's been before, that's kind of what I need to prepare for now. But in our changing environment, we need to prepare for things that there's no memory of. So that's where people in this room can help, Western science, but also our elders know well what can happen. They know places that will be vulnerable in events that have not occurred in living memory or historic memory. So we need to be taking that into account, and we need to be building our communities to be resilient in whatever that means, whether it's energy, security, food security, infrastructure, whatever. And many of you in this room are working on that. Next. And this is the last one, I believe. So this summary slide is supposed to be all the stuff we talked about, right? And I didn't want to do that. So a lot of it's kind of down, right? I want to end this with, that all of us, everyone, can be part of the solution. We know why our environment's changing. We see that with our own eyes. Who are you going to believe? The television or your own eyes? The television or your elders? We know what needs to happen. There's no science research is needed. We know exactly what needs to happen. And I recently came across this definition of hope, which I really like. We got a goal. Do we have a roadmap to get there? And do we have the willpower to implement it? Now, if I want to lose 10 pounds, this is entirely in my control, right? We want to get to net zero emissions as a planet. None of us have complete control over that. But we all have a part to play. We all can contribute. And that, I think, is the most important summary of this presentation is there is hope and we all can contribute. Here's my contact info. I do really want to thank the WAISC Organizing Committee and UAF Bristol Bay Campus for inviting me to present to you. I hope this was useful, and thanks for your attention.
Thank you.
Any questions?
Yeah, so where you were talking about some of the extremes in my graphic, I can't remember the name of it. That trend line that was created, how did you guys end up calculating that trend line?
Oh, I randomly picked that. Well, I didn't randomly pick it. I picked it so it wasn't large, particularly large. So it actually shows a 4, whatever the units are, if you want to call it temperature, 4-degree change increase in the next 80 years. So that's not a large change for say Alaska. But all of that was just for illustrative purposes, just to show how dominant even a moderate trend is in that human lifetime scale.
Is there any evidence to suggest that the Cocktaily fire affected salmon in the stream, whether it be incubating or smoked?
That I don't know. There may be people in the room that might. I don't know that.
So I'm really thinking about, and it came out when you were showing the short-term and long-term cyclicity, and then what happens if you tilt the whole thing. with a trend. And thinking about as we experience a warmer world and large scale changes in the physics, whether we're going to also see new kinds of physical phenomena coming to the fore. And here I'm thinking about heat waves in the sense of very prolonged ocean heating events, surface ocean heating events formed by changes in circulation, air circulation, teleconnection.
So I think the short answer is yes. Some of that will be amplifications of things that have already occurred. They'll just be more extreme. But the emergence of new extremes I think, a certainty. I think Merbach is a perfect example of that. Typhoon Merbach formed in a part of the subtropical Pacific that historically water temperatures are too cold to support tropical cyclone formation. But last year water temperatures there were near record highs. We don't need typhoons to get coastal flooding in the Bering Sea, one of the stormiest regions in the world. But now we've added a wholly new way to do that. If I'd have been here at WAISC last year and you asked me about a typhoon forming west of Wake Island and affecting Western Alaska, I would have said, that doesn't happen. Well, guess what? I can't say that anymore.
One more question.
Thank you for pulling things back up at the end. I really appreciate that. I noticed in the historic temperature change, there was a little bubble over the Anchorage area. Is that all just from geography and rivers, or is there any sort of heat island effect with the city big enough?
Not at this scale.
Thanks.
Thanks, sir.
Great, thank you.